Thank you, and good afternoon. I'm curious, how many of you have ever used Amazon Web Services or have an Amazon Web Services account somewhere? Oh, that's about 1 out of 3 or so. That's not bad. Good. So first of all, I'm a computational physicist. So I spent a lot of my professional years developing tools for people to simulate X-ray absorption in semiconductors, similar to how the people at Unidata here make applications and containerize them up and help other people use them. These days I work at Amazon Web Services, obviously, in a scientific computing team. And so the mission of my team is to go around and help scientists use the cloud for their research work. And also the other way around, help Amazon understand research and the needs of researchers. I'm going to be around all week for the entire workshop. So if you have questions, or if in the hour that is to follow, we don't get around to talking about all the topics I would like to mention to you, then there'll be opportunity to do that later this week. You can just grab me, or I think there are sort of hackathon-y kind of sessions planned into the schedule. So Unidata asked to do basically two things: to talk about new technologies that the user community here ought to be aware of, and to facilitate a kind of skills transfer. So at the end of this talk, hopefully the result is not that you think I'm smart or Jeff Bezos is amazing, but that you feel that you're a little smarter than at the beginning. And we'll see how we do by that metric. For that reason, I have some slides where we talk about results and show pretty pictures, but then there's also uglier, less fashionable slides that talk a little bit more about building blocks. That's a pile of Legos on the slide there. An hour isn't really enough for us for you to be doing demos with me in real time, I don't think. I have sprinkled a number of tutorial exercises throughout the talk. So these are all, each of them lives somewhere on the web. And these materials will all be given to you as I understand it, or I can just give this to the organizers as well, and I'm sure they can get that to you. These are various exercises that would take you something between maybe 15 minutes for the simplest ones to a few hours for the most meaty cases. If you already have an AWS account, then you could attempt any of these things in your own AWS account. You might as well. And I have also created, but I'll show that at the end of the talk, like a temporary user in an existing AWS account that I control, so that people who don't have an account yet can still try to break something and hopefully have a little bit of fun. All right, let's start with a few less technological remarks. So there are two main reasons why I think the cloud is going to have an increasing impact on scientific research. Two primary ways in which it delivers value. And the first one is what startup businesses would call agility, or what you would refer to as the time to science or the time to discovery. And so it's just being able to have the flexibility to try things out fast, to ask questions that maybe you didn't plan and apply for resources for 2 years in advance. Develop and use new technologies quickly. And cloud does that because you can always go and get resources right now. If you need 100 servers right now, then a few minutes can take care of that. Resources can scale to the exact size, so they're not limited by the size of a cluster that lives down the hall from you. And you can leave it to Amazon to do things like update databases and rescale file systems and all that boring stuff that really isn't your forte. You should be focusing on weather and how storms move through the atmosphere and whatnot. The second thing is collaboration. So you all know as data gets bigger, data moves into data lakes and whatnot, that the compute and the people are having to go to the data and collaborate around massive data sets. The cloud, and especially the public cloud, are really built from the ground up to facilitate that, and I think they will fulfill that role more and more. Having a worldwide footprint is part of that. Isolating resources is part of that, so that you can upload a data set and somebody else can unleash compute resources on that without ever eating into your allocation is another part of that. Real-world security is yet another one. You can have the benefits of sharing and have the benefits of security. And public clouds are really, really good at security. Last week we had one of the leaders of the CIA at one of our conferences say that he believes the cloud in AWS on its weakest day is more secure than any on-premises center. You can take him on his word or not, but assume the CIA knows something about security. When I talk about cloud in this talk, I mean the public cloud, like Amazon Web Services. There are also, of course, specific research clouds that are mentioned throughout the presentations here. I think for your mental map, the areas where the difference matters is, first of all, the availability of resources and scale. Something like Amazon Web Services there is a few orders of magnitude bigger than any research cloud that currently exists in the world. And so it can really handle those unforeseen demands when you suddenly need 1,000 servers and you're not going to get in anybody else's way, because that's not a big request for us. The other part is about the data lake model, the analytics, and having building blocks so that you can quickly build new research tools. It takes a company sort of the size of Amazon to constantly be hammering out new semi-managed platforms for machine learning, data analytics, and whatnot, so that you can keep up with the latest developments. That's again something that you need to have a critical mass to do that. We had a really big AWS event just last week. It was our public sector summit in DC. So people from research, education, government, nonprofits were all there. We had about 15,000 people in an unpleasant convention center, as they tend to be at that size. And there were a lot of wonderful talks, including a lot of things that are really related to earth science, to satellite data, to using massive data sets in the cloud. And the presentations from the summit will all go on our YouTube channel probably sometime next week. So if you have some time to kill next week, there will be some exciting stuff to check out. We even had a separate Earth and Space on AWS day, where we had companies talk about streaming satellite data, machine learning on Earth observation data, NASA about exploring space, and so on. So maybe you should consider going yourself next year. Maybe you can come listen to some sessions or even present your own work if you happen to be doing it on AWS. And I want to show you just a few of the things that were presented last week as teasers. So here's a company called Element 84, and they find that there are still too many people out there who just don't know what data exists or how to get to it or how to use it, and they want to bridge that gap. And in particular, they presented some work on how to make Ghost 16 more accessible to a wide community. And they did that using Amazon services, as are listed there. Ghost 16 is basically a demonstration example. Their approach could be used on many different data sets. What it basically is it's an elastic infrastructure that responds to user requests. When the user says, this is the slice of data that I need to see, it'll spin up resources in AWS. They will process the data, create it in the right output formats, make it available, and then the whole system goes back to sleep. And that way, they never have any expenses for infrastructure that's just idle. And the infrastructure looks something like this, where on the, figure out my pointers, on the left-hand side are the original data sets, like Go's. There is a processing infrastructure in between that can come on and turn off as needed. There is a temporary archive where users can stage working data for as long as they're working on it and interested in it. And then through platforms like Pangeo that you're familiar with, users can consume the outputs. And they have a lot of this available in Jupyter notebooks, which I know you all here love greatly. And the result looks something like this. So this is a more pleasant way of looking at Ghost 16 data, obviously, than just looking at a bunch of netcdf files or what have you, on a server somewhere. And you can request certain time slices or stage in your own data or select your favorite hurricane to replay it. So that's one thing that was shown on AWS last week. There was also a company called development seed, and they were using basic image recognition techniques, right? You've all seen this, having computers find the pets in a family photo or so. And they're applying that to satellite information. And in particular, they want to scan and find where all the buildings are so that they can keep track of development, for example, or in a slightly fancier application, what they do is they have the machine learning algorithm recognize all the towers that keep the power, that suspend the power lines, and then they can do real-time mapping of power grids. Same thing that they can track how all the lights are coming in cities and correlate that to development. The same way that they can go and track and recognize crops that are growing in the fields, which then other people want to know because they want to predict where people might run out of food or how the price of commodities might go up or down. And behind the scenes, there's the satellite data. There are users on the far end of that, and in between they've built this engine that spins up an Amazon Web Services to process and deal with all the images. In particular, they developed a utility that can sort of make existing machine learning frameworks like MXNet or Cafe and so on more amenable to using image recognition techniques for satellite data rather than, say, the family photos and the cats and the hot dogs and so on. Okay, enough about fun examples that you could check out on YouTube sometime. One technique I wanted to tell you a little bit about is compute and high-performance computing in the cloud. You might use that, for example, when you run a weather model like WARF or CSM or MPAS or whatnot, all of which have been run on AWS in one place or another. So a lot of different types of high-performance computing already occur on the cloud every day. Genomics and life science is a really big user, but apologies, wrong button. But energy and earth sciences is also a very active field. Here's a slide I'd like to show just to demonstrate the scale of what's possible. So these were researchers at Clemson University who had some natural language processing to do. It's a type of machine learning where you're analyzing and trying to understand language. And they used a cluster tool to come into AWS, to our Virginia data centers, and ramp up a fleet of a 550,000 core compute fleet to crunch through this big machine learning job as fast as they could. It's a little show-offy, but I like to just establish the scale of what's possible. And I used to always use this slide and say, it's only a matter of time before somebody gets to 1 million cores. And what did I find in my mailbox just this morning? It happened yesterday. So the Univa scheduler company, it's a high-performance scheduler, facilitated an EDA, electronic design workload, where again they went into the North Virginia region and spun up 1 million compute cores concurrently on something over 50,000 servers, and got through some kind of massive job. 1 million cores is big, even looking at the higher realms of the top 500 list. Now, what you are likely to encounter in your work is something a little more in the intermediate scale, let's say, of course. Example like this, like somebody at NASA who had a bunch of images of the Sahara Desert, wanted to quantify the biomass, the amount of vegetation. So again, it's a kind of image recognition that needs to happen. If you have only X computers at home and suddenly you would really like to have more for a few weeks, it's nice to come to the cloud and get the work done a lot faster, publish a paper faster, get ready for the conference, move on to the next project. So this is probably the scale that will be of the most interest to you in your work. Like I said, genomics is a very common user of AWS cloud computing. What they really like a lot is that we don't just have regular servers available, but there are also different types of GPU accelerators that you can use. And there are also FPGAs, which is yet another type of accelerator. And in this case, there's this company that used that to set a new record for processing genomes faster than before, and got in the Guinness Book of Records. I don't know if anybody still reads the Guinness Book of Records, but they got in. It was exciting when I was a kid. People still look at that. Yeah. Anyway. Another thing that's cool is that, again, the cloud is a platform for sharing. So as soon as they had figured out how to do this, they put this in our app store as an application, and now everybody else can go and use the same technique and use the same performance. You don't have to reinvent it, and you don't have to buy your own FPGA accelerators. You can just come use them in the cloud when you actually need them. A little closer to home, I was here 2 weeks ago in this very same room, and we had a Wharf user workshop, and we had a tutorial for people to run the Wharf model in the cloud. This was the new 4.0 version, and we ran a prediction we predicted the weather for that same day and then pointed out where it was accurate or inaccurate. The picture here is Kelly from the Wharf user support who was explaining, oh, this is a little faint, explaining why they're interested in supporting Wharf on AWS. And there is, by the way, another tutorial here that you would be able to go through on your own and do the same exercise. GeoSchem is another Earth science code that has also been ported to AWS, and that it's worth checking out because it has a really nice, really well-written documentation where the author is a grad student at Harvard, really takes you step by step exactly through how to launch the calculation and go through all the steps. Both of the tutorials on that last slide were like what you've seen at the last workshop, according to Mohan, where you spin up a server in the EC2 cloud, an EC2 instance, you log on, and you run the program, you run the Wharf program. What will happen to a lot of you probably is that you need to run a model that's just a little bit bigger than that needs more compute cores than fits in a single node. And what you're going to do then is set up a cluster of compute instances, just like you have clusters here, and you probably have clusters at whichever institution you're visiting from. What you see here is a so-called scaling curve, where we are in AWS, and we run a Wharf calculation across the continental US on sort of a somewhat rough grid. We increase the number of compute cores that are used, and we see how much speed up you get as you throw more resources at that calculation. And so in this case, we go up using several thousand cores, and the Wharf model speeds up by a very useful amount. Wharf models, as probably most weather codes, scale somewhat differently depending on what grids you throw at them and what modules you turn on and so on. It's not a simple code, but this is a guideline. Now, I wanted to show you how you do something like this. How do you use a compute cluster to run a weather model? If you've ever opened the AWS console in your web browser, you've seen something like this. There's, I think now, something like 140 different web services, right? So the name is Amazon Web Services. There's something like 140 of them. And so your first thought was probably, holy moly, where do I start, right? The good thing is that for running models, you're really only going to use very few of these services. You're going to probably over time get to know about 5 or so really well, but you can even start with 1 or 2. And at the end of the presentation, I will show you a one-stop guide that helps researchers get started in the cloud and tells you exactly where to start, what to look at, and especially what to ignore. I'm going to go very briefly just through the basics of compute and storage, just to get you familiar with the terms that we use. The people that have had some experience with AWS can take a 3-minute nap at this point, because this will all be very familiar to them. But so let's look at our first Lego bricks at the compute. So you have the choice of a number of server types when you come in and compute in the AWS cloud. There's general purpose. There's compute optimized, which means you have fast cores. Everything else is sort of average, let's say. These are often really great for weather applications. There are also server types that have vast amounts of memory. If you need to run a huge thing in memory, you can get up to 4 terabytes of memory per server. And then there are, of course, the accelerated server types like GPUs and FPGAs. You can look up the hardware specifications for that. For example, the C4 here at the top is one of my favorites. It has 32 threads or 18 physical cores. So it's an 18-core machine. You can already get something done on one of those. And then if you say, all right, let's go with that C4, then you'll have to say how large of a server you want within that server family. You can say, give me a whole node, which is what I often do. But you can also say, this is just a small job, give me half a node or a quarter of a node, I only need a couple cores. Maybe all you're doing is you want to host a thread server on it, then you don't need 18 cores probably. So then you just get a smaller slice, a smaller VM. If you're looking for high performance, then you're typically going to grab the entire server. And if anything doesn't make sense, then please interrupt me. It's all right. What's going to happen then? You say, well, I need some servers. This is the virtual machine image I want to start from. For example, a basic Linux operating system with the Wharf code and some libraries baked in. Set me up 3 servers of that type. And then AWS will go and do that, and a couple minutes later, those servers will be ready for you. They'll be booted with all the things that you specified. Those servers will live somewhere in a data center. Multiple data centers together will form what we call an availability zone. An availability zone is one unit, could be a few buildings chock full of computers. And then several availability zones connected together are what we call a region. For example, we have an Ohio region, we have a Virginia region, and so on. A region is a very resilient thing. These different availability zones are separate enough that if in one of them all the power gets knocked out by the storm of the century, and the next one gets hit by a nuke, the third one will still be up and will still be serving out your data. So this is not like having 3 racks on different floors of a colo building. And then at the global level, there are regions in various parts of the world. So if you're part of a worldwide collaboration, as I'm sure some of you are, then it's nice to have the underlying footprint here where you can have services close to any of your users. That covers the compute. Then you also still need to store your data, of course. There are 2 types of storage that researchers are typically going to use. One is abbreviated as EBS, and that's basically just hard disks that you attach to your compute servers. And the other one is Amazon S3, and that's going to be your long-term storage for your research data. That's the object store where your data sets will live for a long time. There's also a cold storage option for cheap archival of data, and that's called Amazon Glacier. And then, of course, there is also a network that connects all the nodes and all the pieces of your AWS infrastructure together so that they can all communicate with each other. And out of all those pieces, you can then build a compute cluster that will finally be ready to do your high-performance parallel model run. And the compute cluster in the cloud is largely similar to the mental picture that you already have from your past life. The cluster will consist of a head node. That's the place that you log into with SSH. That's where there is going to be a job schedule like Slurm or SGE probably. And then connected to it will be a fleet of compute instances that will do the actual number crunching. It could be 1, it could be 100. And then they have some shared storage attached to them so that everybody can see the same input files and communicate with each other and together write the output back to disk. That cluster is only going to exist probably for as long as you have work for it. Long term, you're going to stage your in and output data again in Amazon S3, where it will live for days or years or however long you want to keep it there. And this is you sitting at home SSHing into the whole thing. There's a lot of moving pieces here, but there are pretty easy ways of setting that up. There are various ways of setting it up, but one that I'm going to show you here is a method called Ulysses Flight. A cluster like we just described will start up in roughly 5 minutes. It'll come with a scheduler and all the tools that you're familiar with, but it's yours. You don't have to share it with anybody. The cores are all yours. There's no queue. You don't have to wait. You can install any software you like, configure it any way you like, and you can grow it and shrink it anytime, or swap out your GPU servers for CPU servers as needed. And when you're done with it, you just destroy it because it's only a virtual resource anyway. You save the output somewhere, and you throw away the cluster. And you can access it just from a command line terminal or via a graphical desktop. And let's see when I'm going to risk my life. Done with these guys. Here is one particularly nice way of launching a cluster in AWS. And it's kind of a two-tier model. What happened here is that somebody, let's say the HPC core group, has predefined clusters for its users. And the user just has to come here and say, start it for me. Quickly copy a code here. So let's say I want to have a grid engine cluster to do my work on. All I have to do is paste in the authorization token that my administrator has given me and say start it for me. Give it a name. Demo Evan presentation. Tell it how to reach me, and say go ahead. And what happens then is that it will launch a cluster for me, and it will tell me by email when it's ready and when I can log in. Now, it takes about 5 minutes, so actually I did the same thing just during lunch break so that we can fast forward these 5 minutes and get into it right now, right? So here's the initial email where it said, we're starting a cluster for you. And then here's the one where it said, hey, your cluster is ready for use. And by the way, this is how you log in, use SSH, and here's a password, and you'll be in. I'm going to show you that in a slightly different view. So here I am looking at my personal Amazon account, and I'm looking at the EC2 service, which is the compute service. And in this compute service, I can see that I have 5 servers running at this time. One is called login, that's the head node of the cluster, and then 4 of them are called compute. So this is a cluster with 4 compute nodes. I can also see the same thing in a slightly different view. So what actually happened behind the scenes is that this Allsys tool sent a long text file to Amazon. And that text file specifies all the nuts and bolts of what constitute a cluster, all the individual pieces. And then Amazon created all of those just based off of that text file. Anybody that you just give that text file to could set up an exact replica of this. And it created a whole bunch of things like, for example, a compute group, a gateway, somewhere in here are compute instances as well. And here again we see, here again it gives me the IP address of the head node, and then see it's a live demo because it asks me if I'm sure I want to connect. And so here I'm logging into the head node of my cluster for the very first time, and so it's doing a little bit of setup there, and then in a few moments it will tell me that it is ready for me. And at this point I can do things like check that I indeed have 4 compute nodes available, Currently, I don't have any jobs in the queue, but I happen to have put some stuff here, just you know, just so that I can demo this for you. I think that will do the job. So what I've done now is I've just chucked about 100 jobs in the queue. And here you see all of them. It just started running the first one, and it'll slowly make its way through the entire list. So that's a cluster that didn't exist 5 minutes ago. Now here it is, and we're working in a parallel environment the way that you're probably used to. Okay, I'm going to end this part. There is a tutorial listed on my slides where you can set up a cluster like this. I can give you some of those access tokens so that you can spin one up, and you can go, for example, through a little tutorial that uses the molecular dynamics code, a NAMD code, and actually I don't really know what it's plotting here, but you, you can go through it and get some work done. By the way, just a general remark here. So there are three main ways to access resources in the AWS cloud. The first is that you're in the web browser and you point and click like I did just now. Make me a server, choose this type, go ahead. The second is that you work on the command line interface where you just type commands in your favorite shell. And the nice thing about that is that those commands can then go into a bash script. You can automate whatever you want. So creating or throwing away a cluster is just an automated action for me that I may do 20 times in a day, right? Because you can just script over it. Finally, there are also SDKs, and so you can build all of this capability into any platform or portal or science gateway that you may have. Again, clusters in the cloud can be fit for purpose. If you're running a numerical model, you may want to have a lot of just fast compute cores, so CPU servers. Then when you have to do visualizations, you may want to have a cluster of GPU instances. You can set up either of them and attach them to your data, which again is living here in S3. The clusters are ephemeral. They go away when you no longer need them, but the data is there forever, or until you decide you no longer want it. The clusters can grow in size. You can just put a flag on a cluster so that when there's a lot of work in the job queue, it automatically provisions more worker nodes so as to get to the work faster. But then when the work is done, it releases all those nodes again because nobody wants to pay for idle cores, obviously. And you can set up a cluster either for tightly coupled or for loosely coupled workloads. If you happen to be doing ensembler runs, then you can always scale horizontally and just do all your members at once because there's near infinite capacity, so you can scale horizontally as much as you want. Right? Okay. All right, enough about clusters. Anybody want to ask questions or tell me that that made no sense whatsoever? No, okay. Let's talk a little bit about data and collaboration around data. By the way, we have these open data is happy data stickers if you want them for your laptop, so you can come steal one later. All right, you all know the basic problem. The data gets too large to ship around, so reverse the workflow, bring the data and the compute jobs to the users. And we already highlighted some reasons why the cloud is a really good platform for doing that. Again, we have the worldwide footprint. Oops, this is a slide I used in Canada last, I guess, and I highlighted the Montreal region to them. Okay, so this is what your data lake actually looks like, right? Here in the center is S3, the main storage service, and this is where all your data lives. Again, the awesome thing about having the data in AWS is that all these services for analytics, for processing, for visualization, for security, for data ingestion and streaming are all sitting right there and can be unleashed by you or by any of your collaborators on that data set without having to do any undifferentiated work like copying data back and forth, provisioning databases, and so on and so forth. Again, this is the thing that very few entities in the world can create, where you need to have a critical mass and be working across all industry verticals like we do to be able to build all these services. Later, when we get to machine learning, I'll show you an example of how those services can actually help you get your work done faster. People like accessing data from the cloud because it's easy to access it. We worked with NOAA 2 years ago to mirror their NextRad data on AWS. And the bar graph here shows the utilization of that data, and then the green thing is what happened when it was mirrored on AWS. The overall usage went way up. Actually, people moved off of NOAA and came to AWS. So this is great. If your research is paid for by taxpayer dollars, then it must feel good that more value is getting out of those data. If you are a publishing scientist, then wouldn't you like to see your citation count go up like that? Anyway, it's good for everybody when data is more accessible and gets used more. We have a public dataset program where we host a selection of very high importance data sets for free. For example, Landsat, NextRad, the Hubble, a bunch of Hubble telescope data just went on there. If you're interested in any of that data, you can go there today and just take it for free and start playing with it and build whatever you like. In particular, we have a nice Amazon.com/Earth website where there's lots of pretty pictures about Earth science data that a lot of you may be interested in. And we have, what should I call it, an inventory called the Registry of Open Data on AWS, where you can also list your own data sets. So if you are putting something in Amazon S3 and you make it available to everybody, you can advertise that here, and people who are looking for data can use this access point to find your data set and learn how to work with it. And let me show that to you briefly in the browser. Here it is. This is what that web page looks like. So here we have something like about 60 data sets in here currently. Here's Sentinel-2. Here's Landsat, also some that you probably don't recognize, Geochem Input, OpenStreetMap, Hubble Telescope, and so on. Well, we're scrolling through, and you'll see that many of the examples, many of the data sets have, let's go back to the top, have a list of links under them. And these are typically examples, use cases, tutorials, things that describe how exactly to use that data, what format it's stored in, and so on. So we only accept data sets in here if they are very well maintained and documented by the data owners. And you would, of course, remain the data owner if you bring your data here. We're merely hosting it for you. Okay. Sorry for flipping in and out of the presentation every 5 seconds. Okay. Who else is putting data on AWS? NASA actually is hosting its image and video library on us. That's where they started with because there was a classic web services problem there, right? Most of the year, not too many people are serving the NASA website, and then there's an eclipse like last summer, and their traffic probably goes up by a factor of 1,000, literally, right? We are built to handle that. It would be kind of silly for NASA to try and engineer a solution to that problem. So they brought data to AWS to solve that problem. Because they don't want to miss that opportunity, right? It's their mission to educate the public. That's this crazy spike, this crazy opportunity that they really don't want to miss out on. So we made sure they could capture it. By the way, NASA over the next couple of years is going to be moving petabytes, tens and hundreds of petabytes of all sorts of valuable data into the cloud. That is coming to AWS. People who want to work on that data or want to build public-facing pipelines and tools on top of that, there's an opportunity for you there. The UK Met Office does something similar, right? So they are sitting on something like 1,000 petabytes of data or so. They're moving a large amount of it to the cloud. They also have to serve data out to all their users, let's say the whole public of all the citizens of the United Kingdom. Again, if there's a severe weather event, you will suddenly see 100 times more requests than normal. You can't afford to miss that, not to serve those requests, because that's their whole reason for being. Again, Amazon Web Services is built to solve problems like that. So they worked with us. Cancer research, so the NIH is building a data commons in the cloud. They're working with multiple cloud providers. We'll be moving a lot of large data sets onto the cloud. You have developed guidelines for researchers to work securely with that data, because there's lots of like DNA data in there, very personal, very sensitive data, and so there are security guidelines that need to be followed. It's a scheme called HIPAA in order to work with that. They're not just dumping the data in the cloud and walking away from it. There are also platforms being developed, mechanisms, and so on, so that people can work productively. Another topic that's important, of course, is containers and microservices. I'm going to say a little bit less about that because it sounds like this community is already deeply immersed in that. You've all been working with containers for years. Another reason is that there are already some nice examples for you to play with if you wanted to. Big Weather Web has been around for a few years. They containerized Wharf a few years ago, and anybody can go and run those containers on AWS and play with them. Tomorrow, I think we also will have a talk from somebody at Jupyter, who will talk about containerized pipelines for climate applications, and you know, those graphics will be prettier than any I can show, so stay tuned for that. We have a batch compute service that's container-based, so if you have any workflows that are based on containers, you can port those workflows into the AWS batch service. The nice thing about that is that it provisions all the underlying resources for you. So all that you would be doing basically is saying, here's my job, it's wrapped up in a Docker, this is how you run it, here's 10,000 of these jobs that need to run, here's all the input files, go away and do it somehow, and don't bother me with the details. And it will do that and bring the results back for you. I'm going to skip a few slides here. Okay. I have a nice tutorial. This is a slightly more advanced one that takes a few hours to work through, but well worth the time if you're interested. And it's an example from genomics. So what happens is that you start with a number of DNA samples taken from some patients, let's say. First of all, what you're going to do is you're going to align those readings. You're going to align that data to a reference genome. Once you've aligned it, you're going to do the variance, which means you're going to find out where it is different from the reference. And then you're going to annotate it, which means that you try to figure out what those differences mean. You're going to put labels on them. So those are 3 separate tasks, and then there is some related QA type task. There are 4 tasks in this workflow that need to happen. Each of them are wrapped in a container, and then those container jobs are tied together by, so the containers live in a container registry. They will be executed through the batch compute service, and the orchestration is done by workflow services, in this case the Lambda and the step function services. The URL is at the bottom here, and it will also be at the last slide. This is a really instructive lab that I would encourage everyone to look at. I will go into it very briefly. Well, actually, I think I've used up a lot of my time. I'm going to not show this one live, and I'm going to move on to the next topic. Serverless computing is a hot topic today. Has anybody worked with serverless computing? About half a person here? Okay, all right. So serverless computing is where you are so lazy that you don't even want to make a computer, but you would just like to send the cloud provider your source code. Send them 200 lines of Python and tell them to run it for you. And that's exactly what we will do. Why would you want to do that? Well, the nice thing about it is it's so lightweight, it's even smaller than a container. And therefore, these actions can start almost instantaneously, right? Let's go back to a time scale. If you want to work on a computer here, you have to go and order that thing from Dell.com or so and wait for it to arrive and whatnot. It takes a long time. Instead, you could go to AWS and say, give me an EC2 instance, I'll work on that. It still takes a few minutes for that instance to be created for you. Maybe you don't have a few minutes. Serverless computing, you get a near instantaneous response. And one of the examples that I have here, it's again something from genomics. It's where basically an interactive process was required. A DNA sample is sent in, and they need to communicate back to the provider very quickly within a minute or so. What are the gene sites where something might be going on? Because Lambda is so quick, because the serverless compute service is so quick, you can scale up a compute response in a second or a fraction of a second and get your processing done quickly. So you get scalability, but you get it on a really short time scale, essentially. The project on the right is a different example of serverless computing. It's called PyWren, and it's a Python library that allows you to use a large number of serverless compute functions at the same time. And this leads to sort of this kind of seeming contradiction where normally a serverless compute action is something pretty small, right? It's a snippet of Python code. But if you use thousands of them at the same time, you can actually get something like a high performance level of activity. And you could be parsing gigabytes of data per second out of storage. And again, your activity could blip from nothing to peak very quickly. And again, we have a tutorial for that you could check out. This was developed by the people at UC Berkeley at the RISE lab, the same people that developed Apache Spark a few years ago. It's a very powerful stuff, and I think all of you who are now excited about containers, I predicted at the next workshop 3 years from now, Mohan will have a slide where he talks about in these 3 years, everybody's jumped on serverless. But we'll see, just a prediction.
That's a misnomer, right?
A misnomer, well, you know, we have servers doing the work under the hood, of course, if that's what you mean. But you don't have to worry about them. That's the idea. Okay. Let's see, so I'll finally say something about the topic that was the actual title announced on the schedule, and I apologize for going so all over the place. So machine learning, it's not only a really big topic for you, it's also a really big topic for us. For example, we collaborate really intensely with these people at Berkeley who are trying to build a new stack that does real-time machine learning, will be used for real-time threat detection and autonomous fleet management and all these modern applications. Machine learning is something that you can start doing on a laptop, right? But if you do it on a laptop, you will have to train on a very small data set. You will have to do a pretty sloppy, rough training job. And so the model that you create won't be all that good. It won't be publishable, and it probably won't have a lot of real-world application. So how do you go beyond what you can do on your laptop? Does that mean that you suddenly have to become an expert who can configure complicated GPU clusters and compile MXNet and whatnot? Or is there perhaps a middle ground where you can have more scale and more flexibility, but you don't have to become a real professional expert? And that's where SageMaker comes in. And because I originally wrote my SageMaker slides with a dark background, I've kept them in a separate PowerPoint file. And we'll go through that right now. There we go. So Amazon lets you engage with machine learning at various levels. At the most hardcore level, you could just get some Linux service from us and build everything yourself. If you're doing fundamental research, that may be what you have to do. One level up from there, you could say, Amazon, give me a cluster of machines that have all the deep learning frameworks, like TensorFlow, precompiled and optimized on them, and I'll work within TensorFlow. That's again something that we offer you. At the very easy end, we have just pure API services just for text-to-speech and image recognition and whatnot, where you have to know almost nothing. But you just chuck 1,000 photos in an S3 location and tell the computer to sort it out somehow. In between that sits the SageMaker platform. And again, that's a magical spot where you have power, but a lot of the difficult work is managed under the hood for you. SageMaker. Fully managed service that enables data scientists like yourself to quickly build machine learning models into production smart applications. All right. And so the different steps of the machine learning cycle, there are always a lot of steps in preparing data, right? A lot of people say that about 70% of what people in the field do is really preparing data. So that's as if I had a 60-minute talk here and 40 minutes of it was spent getting the computer set up, which actually is almost true, except we did it during the lunch break while you weren't here. But still. Then there is actually working with actually doing the training jobs, creating the model, and then there is hosting the model somewhere so that people can make predictions off of that model. So SageMaker has a solution to take care of each of those steps and make them as easy as reasonably possible. So it's an end-to-end machine learning platform. There is nothing for you to set up, and it still gives you a lot of flexibility. You can do anything you can do in MXNet or TensorFlow and so on. Okay. So there are 4 parts to SageMaker. First of all, it's based on notebook instances. So you're going to be doing your work in a Jupyter notebook. And you could even use the SageMaker service just purely to run your notebooks and nothing else, and not even do machine learning. That would be fine. So you will be in a notebook. Then there are built-in algorithms that can do certain popular training jobs in a really efficient way, so that you don't have to spend a lot of time optimizing them. It will execute the training in a managed way, so that you can train across a cluster of GPU servers, for example, without ever having to set up that cluster yourself. And it will host the model for you, so that if you give a talk somewhere and suddenly 1,000 people want to try out what you build, again, we know how to serve things to the web, so we will handle that, and all the traffic will receive a response from your model. And I think instead of showing these slides, I'm just going to skip through a bunch of these and just go back to the console. By the way, the slides will be shared through the organizers, so you will have a chance to look at whatever I've rushed through rather quickly. Let's take a look at the Amazon SageMaker service. Here it is. So I have here a notebook instance in service. A notebook instance is just the server in Amazon where my notebook is living and executes. And so often that can be a pretty small instance, because the notebook themselves often don't do a lot of the heavy work. And I'm just gonna, here you could upload. There's an upload button here. I don't know if you can see that. And so here you can just upload your own Jupyter notebooks and run them. I uploaded one during the lunch break again. And I'm not gonna, just gonna choose a kernel here. Again, you know what this looks like. I just wanna, I have 4 or 5 different SageMaker tutorials, to which again, you're given a link and all the files that you need, and which I can help you run later during the workshop. We can even do like a little group session later during the week if people are interested in that. Again, I just want to point out a few things to you. So this notebook here is pulling in data from the 1,000 genome data sets. Again, this is a massive cutting-edge genomics data set that lives in the AWS Open Data program. If you, again, making the point, if you have your data lake in the cloud, where you put your important data sets, anybody else can be using notebooks and training powerful models right on that gigantic data set without ever having to worry about moving it around. You're doing all that just here from the notebook. There will be a lot of data preparation here that we are not going to worry about. I just want to scroll down to where the training actually happens. Training, here it is. All right. Oh no. Oh no. I'm sorry. An unfortunate click while my back was turned. Okay. So here is where the training is actually happening. And so doing a training job across a deep learning cluster is just a line of Python code at this point. What happens here is that we say do the training on servers of the type C4. So these are, again, servers with fast compute cores, and use 2 of them. If you had a bigger data set, you could just edit this number and change the 2 into 32, change this into fast Volta GPU servers. It would still be the same line of Python code. And you just, again, click enter to execute the cell. Under the hood, we have all these nifty container mechanisms where your training job here will be translated into a container, and that will go on this powerful cluster that we will manage for you for as long as it's needed. We will just return the trained model to you, again as a container, and you will never have to see any of the ugly bits and bobs of that. It's just this line here where you tell us what you need to train on. And then also, if you work through this notebook, you will set up an endpoint and run a few tests and visualizations based off of it. And with that, I'm getting close to the end of my time, so I'm just going to make a few more points to wrap up. I think we can leave SageMaker at that, and I will just make one or two more points in my main deck. Okay. So I meet a lot of people who are interested in using the cloud, but they ask me, all right, so my team hasn't used the cloud before, or the public cloud before. How do we get started? Because the AWS website is sort of overwhelming and confusing. So one thing my team did as part of our mission to help scientists use the cloud is we made the Research Cloud program. And an important part of that is this little thing. It's the handbook for the researcher to the AWS cloud. And what's in that is basically all the foundational concepts, the mental map that you need to have to start working successfully. It tells you first, step by step, how you set up your account and make it secure. And then what are the basic services that you ought to look at. And it'll tell you how do you control your budget, how do you work with data, how do you work with sensitive data, how do you work with compute, how do you set up a cluster. That's something we did earlier in this talk. What should I know about machine learning, and so on. And throughout, because this is just for researchers, we've been able to swap out all the typical use cases about marketing platforms and Disney videos or what have you, and replace them with things that are probably a little more interesting to researchers. So it's all earth science and genomics and astronomy and what have you. And the tutorials that we link to throughout that document, again, are ones that ought to be good for you. So it's sort of written in a serious way, but also with the domain scientist in mind, not the IT administrator. Now, so this book would allow an individual, one ambitious postdoc, let's say, to get started and use the cloud. We also see the question of how do I get started at the institutional level. And to be honest, that's probably the best case if your institution decides to make a concerted effort to help everybody use the cloud as one of your tool sets. In that case, you'll want to build competency throughout the institution. You'll want to have a support team that helps domain scientists decide whether their workflow is good for the cloud or not and how they should get started. And ideally, you would build some kind of platform so that things like integrating with the identity and access management system on-premise or with the billing system and so on are all taken care of for the end user, and they never have to deal with it. One good example is PNNL, not so far from here, who have built competency, and they talk about it in a YouTube video at the reInvent conference last year. And they talk about how they selected projects and helped their research teams get started on AWS. It's well worth watching. Another good example is Emory University. They spoke at our conference last week again. So they built a platform where any of their researchers can just go to this Emory platform, say, I need an AWS account, and within a few minutes, an account will be created for them that integrates with the billing system, that integrates with their credential system, that complies with all the guidelines that they've set out. It's very important, and that ties to support and documentation. And I think something like this is really a recipe for success, and I expect that the platform they built will be copied widely in the near future by others. And with that, I managed to be only 2 minutes over time, I think. Sorry for skipping some of the materials, but I hope I said at least one thing that each of you individually is interested in, and happy to follow up in any way. Thank you. There is not currently a way to say finish it in 1 hour and just figure out how many cores you need for that, no. I think typically people find that out through setting up the problem. They typically need to run smaller tests anyway before they're going to chuck the big one into the queue. But no, it's a good idea.
Could you please use the mic?
So there's the off-peak research that researchers can access in terms of the costs associated with some of the computing. One thing I haven't been able to find any information on is how much of that is available and the sort of overall availability, because it's balanced so that it fits into what the existing computing requirements are on the system. So is there any information out there on sort of like how much you could increase your request on that sort of, because it's done as it's available?
So we do not publish the exact availability, exactly how much capacity we have available. So what the question refers to is there is a class of compute servers that you can ask for that we call spot instances. And it's basically our unused capacity in any moment. It's our buffer, right? But rather than see it go unused, we offer it at a deep discount. Typically, it's between 50 and 80% discounted. So researchers with fixed budgets love to scoop that up because it means you get 2 to 5 times more work done within your fixed budget, right? And so he's asking, well, to what extent can I rely on that being there, I think is the question. So again, we don't publish our capacity because that would lead to people trying to game systems and that would in the end hurt everybody. But these massive jobs that I showed you earlier, the 500,000 and million core jobs, were run entirely within that buffer in a single AWS region. I don't know if that answers the question.
That could answer.
Okay. Thank you very much. Thank you.